All right, now let's look at an example of a more complicated two-dimensional collision. Okay, so we can really kind of use the full framework of solving these change in momentum problems. So let's say we have a particle A, and it's coming in with some velocity v for a collision, and then it gets deflected, and its final velocity we'll say is v over 2. And let's say we also know that this angle is theta. And then we also have our particle B that comes in to the collision, and it comes out at some unknown angle. We'll say initially it also had a velocity v, but we don't know its final velocity. And let's say we also know the angle between A and B initially was v, right? So we know the angle that A gets reflected off at, and we know the angle between A and B initially, but we don't know what B final is. And then let's say we also know we have MA and MB. Okay, so now we're trying to find the final velocity of B. So this, as you can see, is a much more difficult problem than what we had before, because now we have two angles. We have, we're trying to not find the change in momentum of B, we're trying to actually find its final velocity. And not only that, but if we draw what we would normally consider our standard coordinates, where we'd have x and y, okay, we notice that none of the vectors line up with that. But the problem never specified what x and y were. So we're free to choose that on our own. And so because of that, it's much easier to redraw this and say that we have particle A is traveling to the right and then gets deflected. And particle B, there's no way we can get any of the vectors to B to line up necessarily. So we just have to draw it coming off at two different angles and draw our angle phi between A and B. And again, we know this is also V, and this is V over 2. So notice I had the original drawing, but I redrew it because now, since I'm free to do this, I changed my reference frame, so now x is pointed in the same direction as the initial velocity of A. Right? Okay, so now we use our conservation of momentum principle, where we say the mass of A times v, but remember the vector v plus the mass of B, so we'll say this is VA and VB, where both of these, we know that the magnitude of VA is the magnitude of VB is just V. But we keep it separate because conservation of momentum is only true for momentum as a vector. It's not true for the magnitude of the velocities. The magnitude of the momentum is not necessarily conserved. It's just the actual components of the momentum that are conserved. And I think that's a very important point to stress. And so this is going to be equal to the mass of A times the final velocity of A plus the mass of B times the final velocity of B. Okay? So we're given, again, we're given the velocity of A, we're given the initial velocity of B, we're even given the final velocity of A. So the only thing we need to find now is the final velocity of B. So that's good. So we have one equation, we have one unknown, so we should be able to solve that. But first, let's rewrite the equation, plugging everything in. So we have mass A times velocity A, so just V0, plus mass B. So now so the velocity of B, now we have an x component and a y component. The x component is V cosine phi. The y component is V sine phi. And this is equal to the mass of A times the velocity of A final, right, which is v over 2, minus v over 2, because we're going to the left now. So minus v over 2 cosine theta, and the y component is positive, so v over 2 sine theta plus mb final velocity of b. Okay, so now we can just, push everything over to the side, to one side. So over here, we have the mass of A times V. Again, this is the x component, so the mass of A times V of 1 plus 1/2 cosine theta plus mass of B, V, cosine phi, and then the y component, there's no y here, so we have our minus ma v over 2 sine theta plus mb v sine phi. We set this equal to the velocity of b. And so we say, okay, well, is this our answer? Well, so the first thing we do is check our units. So I'm looking for velocity, and oh wait, I have a mass times a velocity, so that's not right. So what did I do? Well, I noticed that I left off the mass that I need to divide this side by. So I also have to multiply by an overall 1 over the mass of b. Okay, so now the masses cancel out, and so I just have a velocity times a number and a velocity times a number, and the same thing for the bottom, so the units check. Okay, so now let's see if this makes sense. So overall, we seem to have something where it's going to be, we have a positive component in the x component because everything here is positive. And sure enough, if we look at this, well, since A is moving to the left, we should have a positive component for our velocity for B. And then if we look at the y component, we see that we have two terms. We have one that's positive and one that's negative. And so, again, this actually, we could have our velocity for B, happen to be like this. It depends on whether or not this term is bigger than this term. And so that's going to really depend on the sine of theta and the sine of phi. And so this does give us the right answer. So everything checks out, so we can see that this is correct. And this is exactly the answer that we should have. Okay, so we've looked at some momentum problems now. I think now it's time to go and start looking at center of mass a little bit, because you'll also have some center of mass problems on your next exam.